a couple of slides I'm just going to repeat from earlier. There are the machines that you will probably be working on will be G80, although now slightly modified architecture in Fermi is also available, and we have, I think, a limited number of those. And essentially you've got a number of processors clubbed into groups, right? And for each group you've got some amount of scratch memory, a cache that is shared across all of the processors, and then the main memory, and the GPU's main memory, and beyond that remains CPU's main memory, which is not being shown in this picture. So system memory is also there, which sits beyond. And in fact, when you read things from the disk, you typically put them in the system memory first, then copy as necessary into this memory. Okay, and this is the Fermi version, and really the only thing, and although I've drawn texture and constant as two blocks here, they go in the other version also. It's just this is a little bit more detailed. The size of scratch is slightly bigger. The number of processors is typically bigger, and the L2 size is bigger and actually gets used. If you recall, in the previous architecture, L2 was not actually being used. The rest of it primarily remains the same, right? So although I'm going to talk about the programming model that is about both, I'm not going to focus on the differences, because mainly you will be programming on the Tesla, the previous architecture. Okay, and just to understand why the programming model is slightly different from what you are used to on the CPU side, look at the architecture. One is that a stark difference between the CPU architecture and on the left hand side and the GPU architecture on the right hand side is the cache. CPU has a big cache, GPU has a small cache, as well as the computation. The green is the computation, and the red is memory, which is divided into the cache and the main memory, so to speak. And the cache on the GPU side is this little red that you see with the oranges, which are the controls. And all the green stuff is the computation, which means there is a lot more area on the chip being devoted to computation at the cost of caching, which means you kind of become responsible for using the limited amount of cache wisely.
So if you have to do binary search, probably GPU is not a good.
It depends. It depends.
You definitely have a big chunk of data which needs to be processed, and the processing is not that much. It's the data size which is large, and because you have a smaller cache and larger.
But remember that for a large size, the CPU's cache is not particularly useful. Right? You go there, then you jump here, then you jump there. It's jumping all over, isn't it? So CPU's cache is not particularly effective for binary search either. Okay, and there are some number of these multiprocessors, and each multiprocessor which are independent, right? It's like having multiple cores, but each of the multiprocessor actually is several SIMD processors, which are not independent. Right? They kind of work together. They're in lockstep effectively, and they're working on same instruction for multiple pieces of data. Okay, here is a slightly more detailed version of one of these multiprocessors. There is a bit of instruction cache. There is this notion of warp, which is the things that get executed together on a SIMD unit. There are two schedulers, so two different warps can get scheduled in the same clock. and then the instruction gets dispatched, and then there is 32 kilobytes of registers available to these processors combined. So the register space is a lot, which means that you can get by running many threads at the same time without worrying about context switching. You can assign some register to this thread, some register to that thread, some to that, and everybody's register is live. The cores are divided into two groups of 16 so that two warps can be done. There is a special function unit which does things like sine, cos, higher order functions, which can be done less fast because there are only 4 of them instead of 16 of the basic operation course. And then that column, which is, none of them are readable, but they have different colors on my monitor. The third column from the left is the load store. So there are 16 load store units which can be loading or storing at 16 different addresses. There is, in Fermi, there is 64 kilobytes of local space, the scratch space, which was 16 kilobytes in the machines you will be using. Fermi also can partition that into a cache and a scratch, which is directly user controlled. So you decide what lives in that cache rather than some predetermined cache replacement policy. And then there is L2 and all that. Okay.
So how many bits for addressing?
How many? The load stores can support 64 bits of addresses. But the current software levels allow for 40 bits of addresses. Okay.
This thing was what part of that big?
So it was one of those multiprocessors.
And
So we have the slices being shown here. Each slice is a multiprocessor. One of these slices is what was in the other picture.
Earlier one was just a notation to show how GPU has a lot more computation than CPU.
Yes, right. That's basically showing the die, approximate die configuration. Cuda is Compute Unified Device Architecture. The programming model is essentially C-centric, C-based, with a few more things, just like in OpenMP. You added a few things to the C to make it parallel. It's kind of similar in principle. Except there you were saying run this many times on the same CPU. Here you are saying run this many times on something else on the GPU. Some of this will probably not make too much sense because they are related to graphics and OpenGL. But essentially, and in fact, I'll probably show you the software stack that's necessary. You're going to need a variant of the compiler that can compile the CUDA specific stuff inside. Okay, and typically it's a wrapper which pre-processes it to extract the CPU parts, uses the standard GCC, CL, whatever you have, to compile those things, and then specific parts that are to be done on CUDA gets compiled separately, and then all gets combined into one executable, or one loaded unit, I should say. Okay. And in some ways, this is basically it, right? Although there are a lot more details that we'll talk about. You've got serial code or whatever, multiprocessor code if you wish, running on one of the cores. And at some point you say, I want to do this 1,000 things on the GPU. Okay, and it is a data parallel model, which means you say, I want to run this function on this data 1,000 times. Okay, and so you can't see the mouse. The parallel kernel device incantation you see is basically saying run a given function so many times with these arguments. These arguments are visible to all of those instances of that function. Okay, and so in this example, parallel kernel would be a function that you have written. Okay, and it is going to be invoked by saying kernel. There are these 3 less than and greater than brackets, which are the things that are added to C, which is going to get extracted by the Cuda compiler, which says how often should this be run. We'll get to details shortly. And then the bracket says these are the arguments sent to be sent to that function. Okay, and then you go back and continue your serial execution. And later on you can do another kernel and so on. Okay, and the picture in the right side says that there is a single thread of control, then this massive multi-threaded thing got executed in parallel, and then your thread of control continues on from there. Okay, it's possible to overlap them, but here you're waiting for the Cuda's computation to compute. You take its result, do some more processing on it, and then say do some more for me.
So you cannot do nesting, right?
You cannot do
Nesting means another parallel kernel.
Inside a kernel?
Yeah.
You can actually, but not in this fashion. As far as the compiler will be concerned, it will still be one kernel. One kernel with only that size. And you have to indirectly, in each one of them, do multiple things.
So in the definition of kernel, we can write these kind of lines.
Which kind of lines?
3 plus.
Yes. Not in the definition of the kernel, in the call to the kernel. Right? There will be the function body, which will be the definition of the kernel, and somewhere else there will be a call to it. So the 3 things is for at the call time.
I'm saying in the definition of a kernel, we can call another kernel. So from nesting point.
The 9 nesting.
No, the compiler doesn't allow that. So you will have to manage that internally inside your kernel.
You have to
Inside the kernel
or something like that, right?
Even spawning is not allowed.
I mean, in a way.
Yeah, effectively that's what you will have to do. You will have to manage it. Okay, and at a high level, it's designed to be a coprocessor. That means you do your main program, and at some point, some function you want to execute. It's an expensive function. It takes too long to compute on the CPU. You say, now do this function, only this function on the GPU. And if I were continuing to do that on the CPU, I'd have to wait a long time before that gets done. But if I send it to CPU, the result will probably come back faster. Okay. There is a separate memory which GPU has. It cannot get data directly from the system memory, which probably will change over time, but right now it cannot, which means every piece of data needs to be transferred, copied by you into the GPU memory before the function will start. Sorry?
Combined CPU with GPU. AG, AMD, they have an architecture which is new. I don't know how it works, but
Yeah, nobody does. This programming model is not very clear at this moment. They're trying to see if OpenCL, which is very CUDA-like, is going to work on it, but it's still work in progress.
And for example, if you are running a complete operating system, and after the initial boot and loading of the drivers, all the user space programs, they are called through these kind of they are called through CUDA. Then is it possible to have running multiple instances of operating system on CUDA? Each single processor is running one particular instance. Something on.
No, it is bad with contexts. It is getting better. So Fermi's context, you can have multiple applications, independent applications, be using Fermi at the same time. But the context switch is expensive, at least from the CPU's standards. It's I think for Fermi it's around 25 microseconds, and for the previous generation it used to be at the range of half a millisecond or so. So as far as the usage is concerned, the intended usage still is that you'll be using one application which will be at one time using this Cuda device. And so if you have lots of different applications using the Cuda device, your parallelism will be affected by all these overheads.
Can you partition the device? So one way is to partition it in like this time slotting. One application uses the complete device for a certain time. But can you do like these many number of cores are being used by this particular application?
That's just a software issue, and it's currently it cannot be done. But without real change to the hardware, this can actually be done. Somebody who's working on the software side will have to find it valuable to do this, but it's possible to do. All right, so the main thing is that it's basically offloading your entire computation, and it's going to be running typically many threads, hundreds, thousands, something of that sort. And a typical Cuda type application will at many places be launching several kernels. Okay? And so that copying of some memory to Cuda, as well as launching beginning of a kernel onto Cuda, is supposed to be as efficient as possible, because otherwise, if it takes too long to send this and do this on Cuda, might as well spend the time doing the computation on the CPU itself. And here is a quick glimpse into the changes to C that Cuda introduces. Okay, there are function type specifiers. Okay, this is called declaration specifications. And a function can be a global, a device, and this is not function. Actually, a piece of memory can be global, device, shared, local, and constant. Okay. Remember those two blocks that I had added on Fermi? One said texture, one said constant. Those are specific partitions of memory. The same DRAM, the global space of memory that is accessible to all of the processors, that gets partitioned into a global memory, a textured memory, and constant memory. Okay. The paths of each of these memory to the multiprocessors are different. Okay. The path from the texture and constant memory is speeded up much faster. It's got its own data path, as a result of which you cannot write to that memory. It's a read-only memory. Once you initialize it, your Cuda program or the multiprocessors individually can read it, cannot write to it. Viewable memory is something you can write to. It is, so to speak, the main memory on Cuda side. Shared memory is the cache, right? The scratch pad that we saw in the architecture. It's much faster. It's almost, for all practical purposes, it is as fast as reading a register. So you can think of 64 kilobytes of additional register space being available, essentially, in principle. So what you see as an example on the right hand side, it says device, float, filter, sum n, right? So float, filter n is regular C. You can add a declaration specification to it, which says that this variable must be allocated on the device. Right? It's not a CPU variable, it's a GPU variable. When you see the global, and by the way, although on the left side, just the keywords that are being added to C are listed. When they are used in a program, there are 2 underscores at the beginning and 2 underscores at the end. So it's underscore, underscore, device, underscore, underscore, to say that it's a device variable. Global void convolve says that it's a function which is visible on both the GPU as well as the CPU. What that means is that you can call it on the CPU, you can run it on the GPU. You'll call it in one of those kernel invocations. All right. The third example, which says shared float region M, is saying that this variable is to be allocated in the shared memory, L1. There are some built-in variables. Right? One built-in variable you always need is your ID, either a function or a variable. Here, instead of function, it's a variable. And so every thread has to know its ID so that you can, if there are 100 things to do, you are number 3, so you do the third thing. Okay. I will get to more detail on the ID, and so it's not a single ID that is provided to you, but it's kind of your location in the space of configurations, and it's not just I've 1,000 things to do, but it may be I've got a 10 by 10 things to do, where each thing is a 20 by 20 thing. Okay, so then your ID is a slightly more complicated thing, right? It's not just number in total count. There are special functions, for example, underscore underscore sync threads. It is a barrier. Barrier in the context of things running on a single multiprocessor. There is, at the moment, no barrier across multiprocessors, except by involving the CPU. All right, and the last line, before the last line, there is allocate of memory. So you can do malloc to get memory on CPU. You can do Cuda malloc to get memory on the GPU. Okay, and you will get some handle to it so that you can then copy from CPU to GPU, or make the copy command, make the copy request on the CPU side. And to launch a function, which is what we call a kernel in Cuda terminology, which will be of global variety. When you have declared a function to be of type global, you can call that function with these 3 brackets, with some information that says how to start this function. Okay, and then some parameter that function takes. Let's look at. We'll stop here. This is the software stack of things that you're going to need. You'll have your Cuda program, right, which is really C with all these things we saw on the last slide added in. And you'll run something called NVCC on it. Okay, it's the wrapper for the compiler that Cuda provides, or sometimes also called the Cuda compiler. It's going to separate out the host code being the basic C, and the GPU code. GPU code, it does something like what Java does. Right? It's got bytecode that a Java virtual machine will run. It's got something called PTX that it generates, which all CUDA devices are supposed to run. Or there is a layer at the bottom that will convert PTX code to the given CUDA device. So PTX code is a bit generic, architecture independent assembly language thing. Okay, and at the end there is this SAS compiler which is going to take the PTX code, generate the machine code for a given architecture that you know at the moment you are running on. And so if you were to say write software and distribute it, and you compile it to PTX, it can be run on all the CUDA machines that people may have. But if you compile it to SAS, or SAS compile it, then it will only run on that specific type of CUDA device on which it has been compiled. Okay, so that's the difference. And at the bottom of it is the driver, the CUDA driver, which is going to take this piece of code that SAS generates and send it to GPU in a form that can then be executed, loaded, executed, and so on and so forth. Okay, so we're going to stop here. We'll look at a few more of the details and then look at a few of the examples next time. Okay, so we were talking about the CUDA software stack, and I'll briefly repeat. So you write, I've given you a very high level picture here. We'll get into some of the nitty-gritties soon enough. But there is a source code you're going to write, probably in a file, probably with an extension .cu to signify that it is a CUDA program. And that will have stuff that gets executed on the CPU as well as stuff that gets executed on the GPU, right? So the general structure is that you've got a CPU program, and in the middle of program, which may be running in a multi-threaded way or a single-threaded way on the GPU, on the CPU side, somewhere along the way, you can say run this thing on the GPU, and then the result will come back, and you'll continue on from there. Okay. And so the same program has code that will execute on GPU, as well as code that will execute on CPU, and this NVCC is the compiler that's going to separate out those two parts. Okay, it's actually a piece of software that has lots of modules or other sub-software that are even individually available. So it calls several things in the pipeline. So it's really a wrapper. That NVCC's main job is to separate out what's the CPU code, what's the GPU code, and for the CPU code, call your Visual Studio, GCC, whatever compiler you may have. Of course, it has to be compatible with the product of NVCC, and most compilers that you use typically are. And then it's going to separate out what's going to execute on GPU. Call proper compilers. There is an intermediate language called PTX. So it's going to compile it, so to speak, into this intermediate architecture independent assembly language. So that's what's indicated here with some foo.s, which can run in on a variety of GPU platforms. And then once you know what GPU platform you're going to run on, you are going to compile it further using OCG, which is essentially an optimized code generator. Right? It's going to take PTX code, optimize it at that point, It will figure out how many registers you have, how to schedule it among the number of different multiprocessors you have, and so on. And then generate the actual assembly language for a given architecture, for a given GPU that you may have. And in the meantime, the CPU has produced the CPU side. Okay, so now you've got two pieces of code. How do they interact? I'll show you shortly, but there is also support for some debugging. Cuda GDB exists, it's an extension to GDB. Cuda has a profiler, so it's going to tell you what function is taking how long. There is recently also a release of something called Parallel Nsight, which plugs into Visual Studio. So you can directly from your Visual Studio debug it, program it, run it, execute it, and so on. Okay, and so this is what's going to happen. The source file is going to have some CPU, some GPU. So GPU is what is being referred to here as the device, CPU as the host. NVCC will separate it out. Depending on the options you give to NVCC, it may compile it all the way to what's called Cubin. Right? It's the object code for a given GPU instance, or to PTX, which is an architecture independent assembly language. And then it's going to also generate host code on which it will either invoke the compiler or simply generate the source code, which you may then at later stage compile. And the application, so there are two modes in which you can do this. The output of NVCC can be one encapsulated library, application, whatever you want to call it. Depends on what flags you give to the compiler. And from the application, you see this GPU piece of code as data. Right? It's got an array filled with some GPU program. And there are functions that Cuda provides. It's Cuda runtime. When you install Cuda, you'll automatically install what is known as Cuda runtime. And Cuda runtime will load this memory array, and you can directly, using Cuda runtime functions, do something with these GPU pieces of code. Okay. Alternatively, you can directly interface with the driver. So every device will typically come with a device driver, which will have some interface, which Cuda drivers also do. And through the driver interface, you can, from your main program, read this encapsulated piece of GPU code and send it to the driver saying, execute this. Okay, so you can do it from an application directly talking to the driver at runtime, or compiled into the application using Cuda runtime functions, call appropriate functions to load the GPU function. Okay, when you create a full GPU CPU program, you typically don't have to do anything. Right? You just have to execute something.exe, and the proper Cuda runtime calls have been made by the library calls you make to make sure that something that gets executed, that is destined for, targeted for GPU, will automatically get sent to GPU, get executed, and the synchronization between CPU and GPU will happen. Okay.
Sir, do you mean to say that even if driver does not exist in some system, then also
Cuda runtime uses the driver, right? Either you can directly talk to the driver, or you make function calls that talks to the driver.
After all, the driver is going to sit in.
Yes, in both cases.
And Cubin is particularly meant for the SM more than 20 architectures, not below that.
Cubin is just a term, just like you say .obj, it's .cubin.
There is some difference between object files of PTX and Cubin.
Absolutely. PTX and Cubin are two different things. PTX is architecture independent, and Cubin is architecture dependent. So you'll generate different qubin for different hardware. And if you have a lower end laptop GPU, your qubin will be different from if you were running on a high-end Tesla, for example. Okay, but PTX also has two versions. They have, because Fermi architecture has some more innovations that Tesla didn't have, and the PTX was not designed to take that into account. So the new PTX is more powerful than the old PTX, but the new software that will take PTX and generate qubin will take old PTX also, right? So if you have legacy PTX code, it will run on new GPUs. It will just not be using the advanced features.
So then what do you mean by that global initialized data in that way?
Global initialized data is as far as CPU is concerned, every piece of GPU code is an array, right? It's data. It's never to be executed on CPU. So it's an initialized data, and you can go read through it in your some CPU program. You can have access to that pointer, but those instructions won't mean anything on CPU, right? So it's, in that sense, it's a data array. The software architecture, basically somewhat of a rehash of the same thing I told you about. There's application sitting at the top. It can talk to CUDA libraries, which would be the most common usage, which in turn will talk to the runtime, and then runtime will be talking to the driver, and driver knows how to talk and interact and synchronize with the GPU, okay? Or the application can directly talk with the CPU, with the driver, which will then eventually talk with the GPU. So all the examples that I'm going to show you will just be the library version. You make library function calls, which the magic is happening in the background. All right. So you're going to need a GPU to run these programs. So the EXE that you will be generating will have the GPU code built in. And that GPU code, as far as CPU is concerned, is just data. However, as long as you have enough things around, that GPU code will run, right? There is a driver and there is a device sitting on the other side of the driver. It's going to work. Okay. It's possible that GPU code is a PTX code, because that's what you instructed NVCC to do. Device driver will compile it to the given device. Okay. It knows how to call the compiler. And that's what is called just-in-time compiling. Okay. The other thing, other than the device and the driver, you really don't need anything to run it. Okay, which means somebody gives you a program, they programmed it, they compiled it, you've got the driver and the device, you can run that program on your machine. Right? That's how people would distribute code, and as long as you've got your driver installed and your machine up, it'll run. If it is PTX compiled. If it is compiled to a specific qubin, specific architecture, then the driver will be able to do nothing. Right? Driver can only say, I've got qubin, I can run it on the GPU, but the GPU will not understand that qubin. So then it won't work. Okay? So this just-in-time compilation business is necessary, especially because unlike CPU, most GPUs there are many GPUs in the market today, which all have slightly different architecture. More than that, on a CPU you will say, I've got a thread to run, and then that thread will run on a core. Here you will say, I've got this code to run, and I want to run it as well as possible. Right? I want to run it on as many processors as are available. I have broken it down into some number of units, and if you've got one GPU processor, you run it on one place, all the units. If you have 10, then however you schedule, it's typically round robin, but you can take the first unit, run it on the first, second unit, run it on the second, and so on. So all of that can be done only if you know how many units there are. All right. When you are compiling, you need a little bit more. When you're developing, you're programming, you need the software toolkit. There are some utility type functions built in. So there's something called QTIL that you will get used to, you'll use often. The library will also have the standard std lib type stuff. You won't have input output because that's not allowed on Cuda directly. But most of the basic stuff, string libraries and stuff will be there. And then you include the proper C header files as well as Cuda's header files. And if you're writing GPU code, you will have access to the same function on the Cuda side. If you're writing CPU code, you'll have access to the same function on the Cuda side. Okay. And so this is the basic way in which it gets done. You write a function. Pretty much it looks like a CPU function. We'll see examples shortly. And you say, run this function so many times. Okay, so in this example, you've got a block of 8 threads running the same function. Okay, those blue blocks, although they seem smaller in the middle, are just scaled down version of the big blue blocks. So they are running the same function. That's why they are called, this style is called single program, multiple data. Okay, they will have their own ID, right, thread ID. And based on that thread ID, they can do different things. They can fetch different pieces of data. They can do different things if they want to. That's why it's not strictly SIMD, but as we have discussed before also, that some of the tightly bound one multiprocessor is designed as SIMD. Right? So all the SPs of a single SM run in a SIMD fashion, meaning that if they have some threads wanting to do X, some other threads wanting to do Y, then there is some magic that will make X happen first, then Y happen for the subsets of threads that want to do X or Y. Okay. You can, and this is what is called a block. Okay, so this is what I was saying, that the scope for sync threads is a block. Here I am only showing that block is a 1D array of threads, but you're allowed to have 2D and 3D array of threads also. What that means is that only thing that it means really at the end of the day is that your index will have I and J as opposed to just I, okay, or I, J and K as opposed to just I. Okay. The idea is that in many applications, especially in scientific computations, you're dealing with a grid of sorts, right? So you have sampled a 2D or a 3D space, and you've said, here, do something with my neighbor's data, do something with my left neighbor's data, do something with my top neighbor's data. You can compute the address of your left, right, top, bottom neighbor using some row major addressing that we are used to. Or you can simply say, if I am ijk, then get I plus 1j, k, ij plus 1k, or ijk plus 1. Right? So this is I, this is j, and this is k. You will see that blocks have a very tightly integrated set of synchronization tools. Right? So they can do a lot together cooperatively. But there are also notions of blocks of blocks. Okay. So you've got an array of blocks now. And the term used for that is a grid. And so you don't necessarily have an array of threads working on a kernel. You have a grid of blocks of threads working on a kernel. Okay. You've got a grid of blocks, meaning there's a block, and again, the grid can be 1D or 2D. And each block in that grid can in itself be a group of threads, which can be organized in 1D, 2D, or 3D fashion. And then each thread runs that kernel. Okay, so now, when you in your kernel, you'll be thinking of what does a thread do, right? Because that every thread is executing the same kernel. So now you have to think in terms of, I have to do this, and there are other members of my block doing whatever they are doing, and then there are other blocks in the grid that are also doing something else. Okay, and you can talk to, as I said, other members in your block in a much more tightly integrated fashion. So there are these usages of, there's something called shared memory. It's similar to shared memory that you know of in from OpenMP days. There is something called global memory, which is also shared memory from the point of view of OpenMP. Okay. The difference is that shared memory is really shared by the block. Okay, its entire life and context is a block. Whereas global memory is shared across the block. It's a grid, different blocks of the grid see the global memory as shared memory. From, again, not using NVIDIA's terminology, but general shared memory terminology. But we will, just so there is no confusion, we will from now on refer to shared memory as that is shared between threads of a block, and global memory as that's shared between threads of different blocks. Okay.
So the blocks can be arbitrarily large, right?
No, they cannot be.
Because last time when we defined shared memory, we talked about the scratch space.
That is shared memory. That scratch space is where shared memory lives. So scratch space we were talking.
That is limited. That memory is limited.
Yes.
But block sizes can be limited by the size of.
Not necessarily, right? You can imagine having blocks that don't use any shared memory at all.
We'll be working sequentially.
Um,
Will there be enough stuff for all the members in a grid to work parallelly? We already have.
as much as possible, right? So if you've got only a block, always runs on a single SM. Okay?
We are further dividing that block into grid.
No. We are dividing grid into blocks. Okay, so block is a tightly integrated group of threads. And that tightly integrated group of threads must run on a single SM. Okay, single SM is just 16 wide SIMD processor. Okay, the different blocks of the same application of the same kernel can execute on different SMs, and that is typically scheduled round robin or something of that sort. Okay, so if you say that I want to run a grid which has 16 blocks, each block having 32 threads, then the 32 thread group will be on one SM. But if you have got 16 SMs, then all the 16 blocks will be scheduled in parallel. But if you had only 8 SMs, then first 8 will be scheduled, and then as they get done, the other 8 will get scheduled on the same SM. Okay.
Each block can do different things. There are no SPMD restrictions on the block.
There is. So SPMD, don't think of it as a restriction. It's more of a programming framework, right? That you, to a kernel, you provide a single function. And that kernel is shared by the entire grid. Now within it, you can check your block ID within a grid or your thread ID within a block and do whatever you wish to do. And in fact, there is really no penalty to be paid if you have different blocks of a grid doing completely different things, because they're running on different processors. But there is some penalty to be paid if within a block you're trying to do different things.
Why do we have these two versions? I mean, so if I just provide a single function in the kernel, then why do I need to say that this is
the differentiation among grid and blocks? Why can't I simply say this is a block of 1,000 or 10,000 threads? It's because you have limitation. The entire block is live in context. You have only 16 processors and 16 kilobytes of register space. And so if you have a program that needs much more than that, each thread needs its own register space, right? And so the more the number of threads, more the size that you have to keep live in context. And hence, there is a maximum size to the block. But sometimes you want to do bigger things, more things. And so then you say, I'll take however many I can fit in one multiprocessor, and then I'll have as many of these as necessary depending on my problem size. Okay.
There's no context switching within blocks. So if a particular block is executing on the same, you finish and then the other block will come in.
No, they are all live. So two blocks that are scheduled on the same SM can both execute. Okay, they are concurrent.
You mean that each block will be executing independently without affecting any other block? Only then we can design our blocks in system.
They can affect in the sense that they share the global memory. If I write one block writes, or a thread of a block writes something to the global memory, a thread of another block shares it, so they can communicate that way. But there is very limited guarantees in terms of memory consistency model across blocks and so on and so forth. Right? You cannot even synchronize across blocks except within a block. So you have lots of stringent guarantees for memory accesses within a block because you can. The hardware allows you to do that. So the programming model essentially is fitted onto the hardware. That's the way it was designed. There are also atomic operations, meaning that when you say add something to global memory or shared memory or wherever, that entire operation, or add one to shared memory, the read of the memory, add one to the data, write the result into the memory, becomes atomic. So no, this cannot be interrupted by another read or seen by interfering with another read. There is also barrier. Again, barrier is really only within a block. There is notion of sync threads, and you can say barrier within a block, but you cannot have a barrier across blocks. And again, it comes from the same reason that all the members of a block are live in context. And if you have many blocks which don't fit on your GPU, that can never execute. Right? A grid has 1000 blocks. You can only fit 3 blocks on a given GPU. Right? So those 3 blocks will run, but they can't be switched out. They're taking up the entire GPU. But if in the middle of that block you say barrier across all of the grid, the other 97 don't get a chance to run. So that grid is done, right? The barrier is done. You can never come out of it.
Did you not say that blocks can be context switched? Entire blocks when you put out if multiple blocks are sharing the same message, then they can context switch.
No. Context switch is only across applications. And there is a significant penalty for that. So 2 applications can both be using CUDA, and that's also only for the recent architecture.
Over here, one block will finish and then the other one.
Yes. No. Multiple blocks can be live, but they don't switch context. Right? They're all live. So I've got 10 blocks that can fit in at the same time. So the scheduler now says, I am free, my adder is free, my ALU is free. Which of those 10 blocks has the next instruction that can be scheduled on that ALU? Okay, they all have their registers ready. All the 10 blocks. So there is no context switching among them.
How can all of them have it ready? So
because there are that many registers. When you
100 example can be there are only 3 live blocks at a time.
3 SMs.
3 SMs. Let's say there are only 3 SMs and 100 blocks. So in that case, the rest of the 97 blocks, do they get to execute? You said no, right? They don't get to execute even a single instruction unless and until the first 3 blocks.
blocks go away.
Exactly.
So those 3 blocks are live.
So the
Right.
97 blocks are not live.
They are not live. There is no switching across from these 3 to those 97. These 3 will complete, or one of them will complete, and then one of those 97 will be scheduled. Okay, but these 3, there is no switching between them, because there is switching of scheduling. Right? There is no switching of context. Everybody is live, and at clock speed, the scheduler is saying whose instruction is ready, right? Whose operands are already on the register in their respective registers, and then some k number of the blocks will be ready, and it's going to execute one of them.
No, but ALU is don't have as many ALUs as
We have 16 ALUs.
SM.
Yes, and there are 2 groups of 16 each, but one warp, which is a subset of a block, executes in 16.
Right. So why does it need to ask who are the ready? I mean,
Because somebody may have read something from memory. The register is not filled with the data yet.
no, but what I want to say is each SM has its own ALU.
Each SM has its own ALU, and each SIMD unit on the SM, there are 16 of them, has its own ALU.
Right.
And in a given clock cycle, on one of those 16 SIMD units, you can execute one instruction for 16 threads. Right? Let me stop, because I think we've come to the end of half an hour, and I'll explain it shortly after.